When determining the density of an ideal gas, you should already know the density equation, which is d, or rho, equals mass divided by volume. You should already know also the equation for an ideal gas, which is piv inert, PV equals nRT. P is pressure, V is volume, N is number of moles, R is the ideal gas constant that corresponds to the pressure unit, and T is the temperature in Kelvin. Somehow, you could combine these two equations to get the derived equation that determines the density of a gas at non-standard conditions, or at standard conditions, for an ideal gas, where you are given the pressure, the R constant, and the temperature, and you can determine the molar mass of the gas. I use mm for molar mass. Some people use a capital M or a script M or whatever. I don't believe there is an official symbol for molar mass, so I tend to use two capital M's to denote the molar mass, which you should know that molar mass has units of grams per mole. Let's take a look at what happens when the density can be determined from other factors rather than just mass and volume. First, understand that volume and density are inversely proportional because density is in the numerator position and volume is in the denominator position. What this means is when the mass is held constant, an increase in volume will lead to a decrease in density. Take a look at these fractions. 1 over 2, 1 over 3, 1 over 4, and 1 over 5. As the denominator gets bigger, from 2 to 3 to 4 to 5, the value of the fraction actually gets smaller because we know that 1/5 is less than 1/2. The volume of a gas can be changed by compression or decompression, which would be a change in volume, by adding or removing moles of gas, which is basically the amount of gas present, and by increasing or decreasing the temperature. Pressure and volume are inversely proportional. If you decrease the volume on a gas by compressing it, then it has a higher pressure. Temperature is directly proportional. Higher temperature, higher volume, and number of moles of gas is also directly proportional. Higher N, higher V. Let's say that our sample of gas is altered by a change in pressure, moles, and temperature. Let's say that it has a system state that has a certain pressure, a certain temperature, a certain number of moles, and as such, it has a certain volume. What I am doing right now is I'm rewriting the ideal gas equation in terms of everything that can solve for V. So it would be dividing both sides by P, giving me N times R times T, all divided by P equals V. Now we're going to substitute nRT over P, which equals V, into the density equation. I will use the symbol D, which is just density. Some people use rho. They're pretty much interchangeable as long as you understand the concept. Density equals mass divided by, and now I'm going to plug in the nRT over P for where V was. Using some tricks from mathematics, we know that a fraction, such as a over b, divided by another fraction, such as c over d, is really the same as the numerator fraction, which is a over b, times the inverse of the denominator fraction, which would be d over c in this case. Our numerator is m over 1, and our denominator, when you flip it, becomes p over nRT. And this is why, when you see me rewrite it, the mass and the pressure will be both numerators, and nRT will be the denominator. So rewritten, the density equals the mass times the pressure divided by the number of moles times the ideal gas constant times T. But if you remember what the molar mass of something is, up here I wrote the molar mass in the units, but let's rewrite an equation for molar mass in terms of the letters that we are seeing on the screen right now. The molar mass of something is the mass that it takes up divided by the number of moles. And the letters do correspond. Grams is the mass unit, and moles is the moles unit. So if you look back at our new step of our derived equation, we actually have an N and an M. M divided by N, which is the mass of a sample divided by the number of moles of that sample, will correspond to the molar mass. So we can rewrite this again. But instead of writing M and N, we can substitute what we're going to do real quick is check the units, because unit checks are really an important skill for making sure that things are working out the way that they are supposed to. Molar mass is in the units of grams divided by moles. I'm replacing the pink molar mass with the yellow grams over moles units. The pressure of something, pressure of a gas, can usually be used with the atmospheres. However, there are many different units for pressure, as you know. We're dividing this all by the gas constant, R, the units of which are liter atmospheres per mole Kelvin. And this is all being divided or multiplied by Kelvin. And we should expect to get units for gas of grams per liter. Let's see what cancels out. Atmospheres is in the numerator position in the numerator and the numerator position in the denominator, so it does cancel out. Moles is in the denominator position in the numerator and the denominator position in the denominator, so they will cancel out. Solely looking at the denominator, Kelvin is in the denominator and the numerator of the denominator, so it will cancel out. If you look at what's left, all we've got is a numerator grams and a denominator numerator liters. So our units do work out perfectly.